Hello. Hello, hello. We've got Gabriella. All right. We've got two dimensions of Sydney. Mason, awesome. All right. We've got Norma in the unanimated version. We've got Melanie. Hello, hello. We've got many more. Those are the people whose visual images I can discern. I'm now going to the chat. Uh, Am I? Yes. Good morning, Angelina. Good morning, Nadine. Good morning, Mohammed. Good morning, Lunar. A friend of yours says hello. Or I say hello. Anyway, morning, Christopher. Awesome. Good morning, Gabriella for the double. Good morning, Effie. Good morning, Melanie for the double. Good morning, Teresa. Good morning, Norma for the double. Good morning, Jean. Good morning, Sydney, who was notably here very early. Thank you. Appreciated. Noted. Good morning, Sinead. Also, I think, well, okay, someone's here. Sorry. Good morning, Jibo. And who else did I miss or who did I miss? Oh, and there's Lunar for the double. And who is it that says hello? I think it's Jada. Is that sound right from my old class? Anyway, whatever. Nadine, hello for the double. Mohammed for the like triple or something. Anyway, hello. We will start physics in a moment. There's more people coming. Lunar has no idea what I'm talking about. Okay. Really? No. Okay. No, I think you have a friend who I taught a couple semesters ago, who I see all the time, and who I think, but I'll get back to you. I'm not trying to call you out in person. I'm just saying we know someone in common.
No, that's okay. I know someone else we know in common who's sitting in my living room right now.
Oh my God, wait, what? Okay, hold on. Wait, who I can see oh, and thank you for by the way, that's points right there. You're talking. Thank you for talking Android video. Wait, who's sitting in your living room right now?
Cheyenne Daniels.
Oh my God. Oh, from the MHC from the Macaulay club from yeah, is that who?
I think so.
Yeah, oh, awesome. Who's sitting here? Awesome. Awesome. All right. Well, then you get excellent. So we travel in similarly impressive circles. Oh, and thank you for talking. Seriously, I feel like I know you like triply well now. Now it means if you ever didn't show up, I would notice it. That's the problem. But no, okay. Okay. So and I see Joshua. Hello. If I didn't say hello, and I think I said hello. All right. And Rebecca, hello. Okay. I know this is a lot. It's all a lot on a Monday morning, but it's to make it feel less like, or it's to transition us into the week. All right, I think that's everybody. I think if I missed you, and you understand, I think you all understand. This is not like, I mean, it's like attendance. Oh, and there's Genesis. Hello. I mean, it's like the opposite of attendance. It's like karmic credit for being here, not a tally of who's not here. Okay, but that's enough of that. I believe I've said hello to everybody. Or certainly I've said hello to everybody that somehow said hello. Like Chanel, hello. I'm not sure I said hello to you at all. There are others. Teresa, if I didn't say hello. Okay. Anyway, okay. So physics, right? We're starting to get more into issues now. Maybe even today we get into a little bit of calculus, believe it or not. A little bit. Um, and I know, but your work is starting to heat up. I'm aware of that. I said this last time. I know it goes, it goes like that. And then you'll have a little break and I'll catch up with you. But yes, it starts to get thicker now that we know sort of what's expected in the class. I think we do. I know we do because you guys are totally on top of your homework and I see that and I appreciate it. There's a couple things I think where you and I, you class, you all of you and I are essentially up to date with each other with on the big stuff. Like your next assignment, is due in 2 days. I had at least, and again on the last assignment, yeah, it's due in 2 days. So why am I confused? It's due in 2 days. Someone asked me, I guess it was on a prior assignment, someone handed in a respectful first draft. This is a good thing, not a bad thing, but I'm still not going to name the person by name. Someone handed in a respectable first draft on the last assignment, and it was respectful. It was neat. It was clear. It was like five-step method. I could see what was going on. It was thoughtful. But the person like totally admitted that they didn't finish the whole thing, that there were certain problems they didn't get to. And they asked, and they wrote like something like, well, something is better than nothing. Like, is it okay if I get this much to you now? Like, could I still have an opportunity to finish later? Totally fair question. And I'm glad someone had this sort of I really appreciate the honesty. Like, here's my honest work, but here I'm honestly not finished, but I honestly want to know, like, but I'm making sure to get this much in before the deadline. So the answer is yes. That's like exactly the right thing to do. I mean, it's a gray area. Like, obviously, if you only hand in one problem or something, okay, that's a little bit pushing your luck. And maybe I don't, then maybe that doesn't like count. But this person's did. And if you do a respect, if you don't finish your first draft, but you're showing respect, you've engaged in it, you've broken through the ice, and you're like trying, but then you run out of time. Yes, no, absolutely. The whole point is I would rather see that before the deadline. And as long as I see that, a respect, there's no exact percentage, but like if it's like more than half, and it's just, if it's intuitively more done than not, yes, you'll get the same points that everybody else got for getting in on time, and you'll get the opportunity to later finish and revise and get all the rest of the points. That is correct. And I want everybody to know that. Because you'll see as the physics gets like you're already, some of you, I'm asking you to already think about problems and do things that are starting to get challenging for some of you. Like some of you, maybe all of you, some of you are very, if you're thinking to yourself, like, wait, what is happening here? Like a second ago, I was like, distance and displacement. Like, and now I'm like, what? Acceleration? He hasn't even said anything about acceleration yet. I know. I'm here again to say, and I'm going to stop. We'll get to it. But more and more, it's going to feel that way. More and more physics does feel that way. But it feels that way to everybody, including people that do physics for a long time. So the idea is you want to be able to break the ice on this stuff and like confront it and try even when it seems over your head. And as long as you get what I'm saying, okay? But I've just that's the so those of you, even those of you like 4 or 5 of you, I'm not going to mention names right now. I almost want to because it's a positive thing, but like 4 or 5 of you have already handed in something for midpoint velocity, the homework or whatever it's called. It's due on Wednesday. So you've already gotten a bunch of points, please, like 24 out of 30 or something like that. Again, please know, because I know it's an unusual grading system. You're not missing 6 points. You didn't get deducted 6 points. I haven't even looked at the details yet. It's 24 means, wow, you're already in. You've made a really good attempt. It's amazing. You're now in a position to get all the rest of the points, as we go and as we discuss. Okay, I think everybody gets it. But so I think and I could tell, like, I think you guys do get it. You're handing things in. So there are a couple of stragglers still that I owe you. Like, there's a couple of redos on number line on the first one. There's a couple of redos on the second one or train a lot. If you haven't gotten that back, I know that. Maybe I'll read the names at the end of class. If you want to stick around and find out, like, that's fine. As long if you want to just find out, wait, did you get this for me? Because I haven't gotten back it, you can. But I'm telling you, yes, there's a couple redos that I've not gotten back yet. I honestly, as the semester progresses, I'm going to put more of my thinking into the redos than the originals. Because by the time it's a redo and you're going for all the points, then I think you're saying, I feel like I'm doing this right here. So we're talking about micro correction. You get my point. All right. All right. But anyway, good job. I think we're all together. So it's time for me to start ramping up some more physics. I'm looking in the chat. Is there something? Oh, okay. I see the direct chat. That's awesome. Sent it. Got it. Thank you, direct chat person. And Chanel, good morning. Thank you. Genesis, thank you. Good morning. Okay. So I think, and the way you're using the chat, I think we're all together on it. Let me also repeat, because I was just like jabbering with one person in the class, like on a social way, about someone else of her, a friend of hers that I know. How do I know a friend of her? Well, I mean, I taught her 2 semesters, but please remember Tuesday afternoons. Wait, there's something in the chat. I'll check. Tuesday afternoons. What, like I finish teaching at 1:30, beginning of community hour. Generally speaking, last week was rough, but generally speaking, from 1:30 sort of on, like not just for community hour, but like on, it seems to be the routine now, till 5 or so. I'm in my office on the fourth floor, and so it's kind of like extended office hours if you like, or it's in, I mean, the time to find me and for me to get to know you better or help or whatever is Tuesday afternoons. It's a somewhat expansive stretch of time. It's only one day, so just text me to say I'm coming just to check. Like, are you there? Do you have a million people in your office? I'm coming. Okay, but Tuesday afternoons is the time, which is tomorrow. Okay, okay. Chat. Good morning, George. Awesome. Thank you. Okay. So I think we're good. Um, yeah, I think okay, in my mind. Okay, as usual, the equations on the board, just to be clear, the equations on the board right now, that's where the ship is heading. I don't want to fool you. I don't believe I've said anything about them yet. I think that's where the ship is now heading. They are, with regard to homework number three, average acceleration. I want to get rolling on that and start getting really kind of more mathematical with you guys. And then once we're sort of in the thick of the math, then we'll take a step back, whether it's this coming Wednesday or next Monday, and we'll talk about the train of thought thing. I promise you didn't do that for no reason. We will. It's very important to discuss, but I think you'll find it more of a relief and you'll see where it fits in more. You'll appreciate it more if it is a little bit of a break once we go. And I think you'll also I think some of you want to see how this math and stuff works for these harder homeworks. So we're going to stay with the harder homeworks right now, the quantitative homeworks right now. Then we'll go back to train of thought, like probably next week. So everything that's on the board now is about what we're going to need to talk about homework three and four, average acceleration and midpoint velocity. So I haven't said them yet, but that's where my ship is heading. Okay, so hold on one second. So, um, okay, I'm just looking at the chat. Okay, okay, I'm gonna switch the board. Um, well, all right. I'm just gonna get to wait, I'm gonna pose a screen share. Pardon me for a second. Where'd it go? Hold on. Just screen. Eh, right, right. Okay. So quick, just so we know where we're at. So we know where we're at. Okay, this is what I'm talking about here, right? This sheet. This is what I'm about to go over right now. Oh, it says Professor Bean doesn't work with us anymore. You may meet him again someday, whatever. Great guy. So he helped me sort of clean up this sheet. Okay, so this is what I'm going to go over. Obviously, I'm just screen. If nothing else, I'm doing this so that if you happen to be watching this video later for review, or you weren't here today, like you can screenshot this or you screenshot it now, I guess, whatever. But that's what we're talking about now. I want to get. Well, all right, here. Vocally, I'll tell you right now, the very quick review is supposed to be a review, right? So the one thing when you hand in your, I would expect a diagram for this. I would expect even though it's going to be very simple, step one, diagram fact pattern. Even though it's going to be a very simple diagram, the key to the diagram, as we're going to see more and more in physics, the key to the diagram really is that not only will you label north and south somehow in your diagram, but then you need to designate in the diagram, you need to choose a coordinate system and you need to consciously choose which is positive and which is negative, right? Because that's what we're really kind of doing at this early stage of physics is sort of translating English into symbols, right? So one way is north and one way is south, okay, but now you are making an assignment of which one you're going to call positive and which one you're going to call negative for the sake of the numbers. And that is honestly up to you. And either one will work as long as you're self-consistent, but you have to make a choice. That's really what the train of thought thing is ultimately getting at. You get a bunch of choices in physics that are more choices than you might have guessed, but you don't have a choice but to make those choices, if that makes sense. Okay, so you have in your diagram here, designate which one is positive, which one's negative. I'm just going to say I'm calling north positive. That's traditional. But you have to know which one you're doing. So if I say that north is positive, then the total distance for this journey is 700, is positive 700 miles. Stop me if I'm going too fast. I'm just trying to blast through this so we can get to like the harder stuff. What's the total displacement for this journey? If she's flying from Berlin to Rome. And if I called Rome negative, if Rome is south and I call that negative, then the total displacement is negative 700 miles, correct? Stop me if it's no. What's our average speed for the journey? 700 miles divided by 4 hours. In other words, 175 miles per hour. That's the average speed. What's the average velocity? Negative 175 miles per hour. Okay, so that's the answers to. Oh, there's something in the chat. Hang on. Sorry, something in the chat. Oh, that's a yes. Yes means you agree. Oh, thank you, Gabrielle. That is total points. Assuming I understand your yes. If that's like means go on, and you can triple dip that. That means like I can go on. Blah blah blah. Thank you, Gabrielle. Do I see you? Is there also video? Okay, so that's one. All right, now instantaneous velocity. There's something else in the chat. Sorry. Oh, okay, great. Oh, direct chat. Can I say that again? Yes. Sorry, I'm speaking. Yes, I can say that again. Also, direct chat person who's asking me if I can say that again, that counts as please go back. That is a portal. You get points for the okay. And so thank you. But now, can I say which again? I'm not sure which one you mean. Um, the answers that I was saying were A, 175 miles, B, negative 175. I'm sorry. A is 700 miles, B is negative 700 miles, C is 175 miles per hour, D is negative 175 miles per hour. Person in the direct chat, can you just let me know? Is that what you were at? Does that do it or you? I'm happy to do it again. Awesome. Terrific. All right, thank you. And that counts as closing a conversational path. There's points for that as well. I'm saying this, I won't keep saying this for 2 semesters. I know it's boring some of you, but I want all you to understand how this works. It's like Animal Crossing. Like every time you do a thing that helps the class, that helps me teach you better, you just submit in that portal and you get points for it. It's a win-win for all of us. So the person that just asked me questions in direct chat and then affirmed that the answers helped him or her, like that's super helpful. So okay, you get it. And then there's something else in the direct chat. I'm just looking, and I want you to know I respect the direct. I love the direct chat for this reason. It's the one thing we can't do in a real class. Um, you're good. Okay, awesome. And thank you, direct chat. Okay, that's two direct chat people. Okay, so that's one review. That's about displacement and average velocity. Okay, then two, we're all of a sudden just introducing a new concept. There's no text, I mean, there's a text, but there's no like big reading. Just all of a sudden it brings us to a new concept. This is the way physics works. It's because if our mind sits at the old concept long enough, honestly, any one of us, if we had nothing else going on, would get bored of the old concept and our mind would naturally start expanding it to, but what about if this situation? So here's what's going on in the next one. Now it's talking about instantaneous velocity, not average velocity. New concept. I'm going to switch the board now and start writing about it. Now, I mean, when I say new, you've seen this before, maybe in high school physics, but certainly in calculus, you've seen this. It's not, but I'm saying it's new in our progress through physics. So wait, so I'm going to switch the board. But this is where calculus thinking becomes important. But I'm switching the board. How am I switching the board? I'm going like this. Okay. And I'm even going to, because I'm using the board now, a new thing also. I'll look later if this, for some people, this will work better. Whoops, sorry, what I'm about to do. Some people it won't. You'll tell me later. I just did something for the sake of the recording. I just made the board bigger for the sake of the recording. So hopefully that will help. Some of you have commented on it. Hopefully that will help you later. Um, it means I can't see as much temporarily, but I will look again. All right. So here's yeah. Okay. Okay, let me start by saying, so I'm backing up. So I'm like teaching now, okay? There's a concept of average velocity. V bar equals triple equal sign x minus x naught over t. Average velocity is total displacement between 2 points in time. Here's something where you might want to write these things down. I'm not going to say this, but if you write them down and submit to the note-taking portal. Average velocity is displacement between 2 points in space, right? Like final position minus initial position. So average velocity is the difference between 2 points in space divided by the difference between 2 points in time. Average velocity is an interval divided by an interval. The advantage, well, as opposed to, we're now going to define instantaneous velocity, which is velocity at one point in space and time. Average is the intervals between 2 points in space and time. Instantaneous velocity is the quantity, the measurement at one point. Now, that's a huge distinction. Let me, quick overview, and that distinction comes up in physics all the time. Intervals between points versus quantities at points. Now, something maybe to write down that I won't is the advantage of interval measurements. The reason any physics study starts with average velocity, displacement over time interval, is because intervals between points are actually more accessible to measurement and to the mind. We can measure. Sorry. Good chat. I mean, good something in the chat. Can I define instantaneous velocity one more time? Yes, in English, instantaneous velocity is velocity at one point in space, 1 point in time. Now, now I'm not going to repeat that too many times because actually that's English. You're going to see in a minute that I need to do better than that. I actually need to give you a better definition than that, a more mathematical one in a moment. You're going to see. So you don't need, but the basic idea is that average is between points and instantaneous is at a point. I mean, instantaneous means at instant. Instant means 1 point in time. Now I'm just giving a quick, so hopefully that helped. I'm just quick overview here of like why we're making this shift. We started with averages because those, oh, great. I love it. All right. Thank you. Okay. Um, I have to open up a portal for just like sense of humor too, but okay. It helps all of us. We started with average because you can actually measure how far something went from here to there, or you can measure how great a distance it is or displacement from here to there. And you can measure how much time elapsed from here to there. Also, you can picture it in your mind. Oh, like 3 miles in 1 hour means 3 miles per hour. So averages are more accessible to tools of measurement and to the mind. Like you can visualize them. However, as some of you may have already noticed in some of the prior problems, they're called averages for a reason. They're averages. They're less exact. If I say something went 30 miles an hour and it took 2 hours to do it, then on average, its speed is 15 miles an hour. But that doesn't tell you how fast the thing is going at any given moment. Like, right? So at any given moment, so when the cop pulls me over for driving past a school and says, "Do you know how fast you were just going past that school zone?" Well, I could say, as a physics professor, I could say, "Well, I wasn't looking at the speedometer, officer, but like I have been in the car for 2 hours and I've only actually accomplished like a 10-mile journey. Granted, I sat at a rest stop for like most of it, and I went backwards for a little part also when I was lost. But I know I've only actually accomplished like whatever I just said, like, 10 miles. And I've been driving for 2 hours. So I guess 10 divided by two on average, I guess I'd be going 5 miles an hour, officer. So I don't see what the problem is. Right? Like, I would never do that. Okay. The physics is correct, but that's an insane thing to say to an officer because that's not what the officer's asking. The officer doesn't want to know how, on average, how fast I was going. He wants to know if I know, or she wants to know if I know how fast I was just going when I passed the school or whatever, right? And the cop car, the police car, right? So averages are actually easier to measure and easier to compute and easier to visualize, but they're not exact. They don't tell you what's going at it. So we need this other concept. We need a concept called instantaneous. We need to know what's going on at a point. And that's where we're getting now in physics, right? Okay, but like somebody in the chat asked, wait, can you repeat the definition? So the loose definition of instantaneous velocity is how fast you're going or something's going at a point in space at a point in time. Yeah, so looking at the chat, hold on, I'm going to pause. So looking at yes, yes. So instantaneous means specific at a certain time. Thank you, George. And George went public. So awesome, awesome. And totally submit for points for that. Yes. However, yes, but there's a problem with that. There's a problem with that. Like what fastness means, how far per how long, right? Like fastness means how far you got in a certain amount of time. Like you divide displacement by time to get fastness. But if we're now just going to talk at a moment, if we're talking at a moment, that's not an interval between 2 points, that's a point. So no time has passed. And in no time, you go no distance, presumably. If instantaneous is exactly, literally, how far you went in, at 1 p.m. and 0 seconds, you didn't go anywhere at 1 p.m. and 0 seconds. To get somewhere, we had to at least wait till 1 p.m. and 1 millisecond or so, right? So in other words, wait here, I'm gonna write this in red so you know it's not actually right. I mean, if we just stopped right now, if I just said, okay, so velocity at an instantaneous velocity is velocity at a point in space and time, which I am repeating to the people in direct chat who asked me to repeat, like, is that what you're saying? Well, yes, I am saying that, but I can't stop there. I can't just say instantaneous velocity v with no bar over it, like not average v, actual velocity. I can't just say that it's how far you went at a moment in time, because if you really think it through, at a point in time, you will only be at a position in space. So your interval would always just be 0 over 0 if we just left our analysis there. And 0 over 0 can't be the answer. Like if the cop pulls me over, the police officer pulls me over and says, "Do you know how fast?" And he goes, and I gave the whole stupid speech I gave a minute ago, and they're like, "No, no, 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 dude, don't give me that physics garbage." Like, I'm not asking about your average over the last 3 hours. I'm asking when you just passed my radar gun outside the school, how freaking fast do you like? What did your speedometer say at that moment, dude? Don't mess with me, right? Fair question. So, but then if I go, well, right at that moment, I mean, the clock hadn't ticked at all at that moment. And so I hadn't gone anywhere. I mean, right at that moment was like a snapshot. Like you're asking, what was I doing in the frame of the movie of life? Well, I went nowhere in no time. 0 over 0, sir. It's 0 over 0. And by the way, no matter what I was doing, I would say 0 over 0, even in a Ferrari. I'm 0 over 0. And then I would say to the officer, and by the way, I don't know what you're going to do with that. I don't know how you're going to write me a ticket for 0 over 0 because you may know this, officer, but 0 over anything is 0. Well, I would never do that, clearly. Okay. Like, because especially the officer might have gone to John Jay. And then the officer might say to me, oh, yeah, 0 over anything is 0, smart guy. Well, anything over 0 is undefined infinity. So I guess you were going infinite, like the Little Red Riding Hood problem. Anything over 0 is infinite speed. So you were going infinite speed. So I guess I'll write you a ticket for $1 bajillion, smart guy. Or then someone else in the car might say, like, actually, anything over anything is one. So I guess he was going 1 mile an hour. Or actually, I guess for that matter, he was going one like light year per hour. So that's freaking fast. So write him a like, that's insane. It's not 0 over 0. So what is it? Well, this is where calculus comes in. This is where physics cannot go very far without calculus. This is part of why you had to take calculus to take this class. Now, to do a lot of calculus exercises and a lot of calculus procedures and hard and integration, all this, that gets thick in physics 204. It's not going to get that thick just yet as far as calculus procedures yet. But you have to be somewhat familiar or wrestled your mind with some of the calculus concepts, such as limit and derivative. Because what we're really going to say here is from like, okay, first of all, so what I'm saying here, and by the way, I'm just teaching now. All of this stuff that I'm saying, you did not have to think about all of this or realize all this in order to do the next question on the sheet, by the way. I mean, maybe I'm doing this in the wrong order. I'm going to show you the answer to the question on the sheet, and you're going to see, well, I'm going to tell you right now. The answer on the sheet, sorry, I should have just said it right away. The answer on the sheet, number two, is 80, sorry. Yeah, is 80 miles an hour. Okay. The answer to, sorry, I should have just said that. The answer to question two on the sheet is 80 miles an hour. And I believe that you could get that without all the stuff that I'm saying right now. I'm saying all this now to fill in and whatever, to teach you. But and similarly, well, okay, I'm just going to say this. I know I'm going a little bit, but for those of you who are looking for satisfaction or closure or to see how the class works, I believe the answer to number two is 80 miles per hour. I'm going to explain why in a couple of minutes. Um, but it is 40 miles divided by half of an hour. Um, and then, by the way, I believe the answer to 3A is 30 miles per hour per minute. Okay. Just to be clear that you can get these without thinking of all of this stuff. You can get these with just the definitions on the sheets. But now I'm trying to back up and help you more for the further problems. Okay. I'll go on and say that maybe at the end of the class, I'll just bang through the answers. But anyway, just so I'm not trying to confuse, but I'm going to go back to this discussion now, though. I am saying from now on, when we write V without a bar on top of it, we mean instantaneous velocity, not average velocity. View that, okay? Now, what does that actually mean, mathematical? What it really means is the limit as t approaches zero of average velocity. Instantaneous velocity is the limit of average velocity. It, and you've seen this, and this is, and I could believe me, if I'm not careful, I could talk for days about what I really mean by a limit and all of that. But and I might at some point. But the idea is that you have taken calculus. So if you picture if you picture a car doing something in time, going forward at different rates in time, maybe it'll even turn around and go backwards at some point. If you picture the graph of position with respect to time of some particle, some car or something, the average velocity, the average velocity of the car is the slope of the line segment connecting 2 points on that graph. Right? Because average velocity is displacement over time. It's the rise of that graph over the run of that graph. Excuse me, it's the rise of a straight line over the run of that straight line connecting any 2 points on that graph. What instantaneous velocity is the slope of that line in the limit as you bring the 2 points arbitrarily close to each other, as close as you can get to each other without them being 1 point, right? That's what a limit means. Let me just see if there's any other way to say this. So, in other words, instantaneous velocity is not actually the rate at a point. That would always be zero over zero. It's the rate in the limit as the 2 points get as close as they can get to being 1 point without actually being 1 point, right? Put another way like this. You could say delta t, or I'm using delta t and t interchangeably because because I'm always assuming that t naught, the first t is always zero. So either one I write is okay. But just to I'm going to say this very quickly. So I'm saying we're now involving limits. I'm not saying you have to do a bunch of calculations or proofs with limits, but I'm saying you have to be able to picture them from calculus. And the thing to picture about limits is that the thing that's weird about limits is they seem very mathematical and very, I know, excuse me, they don't, they seem very philosophical and very vague at first. They seem sort of the opposite of math to a lot of us. Like a lot of us, even if we say we don't like math, at least what we do like about math is that it's sort of black and white and clear, and we know when we're wrong and we know when we're right. And it's right, it can be sort of comforting in that way that it's not, doesn't seem like a matter of opinion or something. So sometimes math, but then when we get to limits, if you're anything like me, when I first got to limits, I was like, wait, what? The 2 points are as close as they can be together to almost be 1 point, but without actually being 1 point, that sounds very vague and weird to me. Like that sounds like you're having it both ways, math people. It sounds that way. It sounds that way, but it actually isn't. It's actually super precise. What a limit is super precise and is actually best understood. Okay, so right now, what I'm saying, I know I'm a little bit jumping around. What I'm saying is to understand instantaneous velocity from now on, what we mean is average velocity, but in the limit as the time interval goes to zero. When the time interval but when the gap between the two time points is as small as it can be without actually being zero. That's what limit means, right? Now, again, I'm going to say in a pure math class, when someone said that to me, that it's there, the 2 points are as close as they can be without being 1 point, I personally, or at least unconsciously, I was like, what? Like, that does not sound like mathematics to me. Like, what do you, as close as can be without actually being zero? What? But here, think of it as a scientist, though. If you think of it as a physicist or a scientist, it actually does mean something. What limit actually means is what, well, that what that says, after all my big point, you can't even read my handwriting. It says a time interval big enough to affect measurements, but too small to measure. A time interval. So as t approach the limit, as t approaches zero, what that really means in physics is you're talking about a time interval between two events, a time interval that's big enough for something to happen, a time interval that's big enough for a car to go from somewhere to somewhere else, right? Now, it might be really, really small. It might be a millisecond. But if a car, so that where the car goes in a millisecond is only like a millimeter, but a millimeter, or let's say 2 milli, whatever. Yeah, like say it's 2 millimeters. Like it's a millisecond, and the car only goes 2 millimeters in that second. Now that's all very, very tiny, but it's big enough numbers to do math. 2 millimeters divided by 1 millisecond is 2 meters per second of velocity. That's real velocity. That's like 4.5 miles an hour. That's like a real number. I mean, in the realistic world. And I see the chat. I'm totally psyched. I'll get in 1 second. But what I'm saying now, if you're like me, I don't. If you had an experience kind of like I did, if you spent a month of your first calculus class, like playing with limits and all these asymptotes and jump discontinuities and all this stuff. I mean, I love it now. I'm not making fun of it at all, and I'm certainly not making fun of your math teacher. Like nothing but respect for your math professor, like for real. But if you're like me, all that stuff was like, what? And maybe you did it well, but you didn't know what you were doing if you were like me, or maybe you didn't do it well like me some years. But what I'm saying to you now is that limits, what they mean, and I will get the chat in a second, but a limit as time approaches zero, when it comes to like something like speedometer or something, what we're saying is an amount of time that's big enough that a car will move in that time so we can get numbers so we can divide them and get a realistic like the car's going 50 miles an hour people or whatever, but small enough that it's below the threshold of measurement, i.e., if I'm a policeman or whatever, woman or whatever, I have measuring, or I'm just in the lab doing physics. I have measuring equipment. It has notches on it. Like my clock only goes to a certain number of digits. My stopwatch only goes to a certain number of digits right after the decimal point. Anything after those digits, things are happening, but I cannot quantify them, right? So what's ever happening in the digits that I don't see, but they're happening. That's what we mean by the limit as we approach zero. We mean intervals that are big enough to affect stuff, but too small to quantify. And an instantaneous velocity is a motion in an interval that is big enough to mean something, but too small for us actually to put numbers to. So we have to extrapolate it or interpolate it from larger context or do cool things like calculus to figure it out. That's what a limit is. It's real. It's not BS. It means you've got to have something that we're looking at, but raw measurement ain't going to get us there. So we have to do analytical tools. In other words, bottom line, and I'll shut up because I know there's at least one thing in the chat. This is my quick, like, what calculus means once you're actually using it in science or whatever. Okay, this is not going to help right now. What I'm saying isn't going to help you do a million calculus exercises, but it might start putting in perspective the exercises that you have been doing in your life. I am saying that that business of this interval is too small to find 2 points on the graph. Like if I made the 2 points on the graph are so close to each other, if I made them any closer, like my pencil would smudge them into one, right? So I can't even draw a line between them and get its slope. So what do I have to do? Something else. I take the slope of the line tangent to the curve at that point. And that gets me how steep the curve is at that point, right? And whether you're thinking of cars on the high, so instantaneous velocity is something real in the real world, right? When the police officer is asking you, do you know how fast you were just going? They're asking you a real question that actually obviously the car was doing something a moment ago. But if you just think of it as how fast was the car going divided by how much time elapsed, that would be like trying to take the slope of a line between one point. How do you do that? So you got to do something else. You've got to draw a tangent line to the curve and take the slope of that line. That will be how steep the curve is going. Like, what's the steepness of the curve at that point? In other words, it's real, it exists. The slope of the curve at a point exists. It's just that we can't get at it from a conventional method. So we use a limit. And the limit means real, but below the threshold of measurement. And everything is what the difference between physics and math is that physics is math in a way, but everything that we're inputting into all the mathematical functions comes from the real world of measurement. That right? Okay, I'm going to pause for a second because there's at least one thing in the chat. But this is okay. It's like perspective moment. Sorry, and if I have to back up the homework and give you more time on that, I will. Don't worry. Like I know I'm talking a lot. Hold on. Oh, the handwriting. Yeah, no, I'm sorry. The handwriting it's hideous. Um, I'm going to write it one more time on the next page, and then I'm going to move on. But you're absolutely right. that also counts for points. You should. So I'm saying, what do we mean when we say the limit as t approaches zero from now on? We mean a time interval. Oh, that's just as bad handwriting. We mean so I'll read this. I don't know if that actually improved it. It made it bigger. You probably still can't read it. Hold on. Sorry. What I'm saying, though, what I'm writing, and tell me honestly, chat person or other people, if you can read this now. I'm saying a time limit as t approaches zero is a time interval that is big enough to affect measurements, like big enough for things to happen in it, like things could move in that time interval, but too small to actually measure, meaning it's below, it's between the curve. Oh, great. Okay. Thank you. So, and why I'm dwelling on this, folks, to me, this is the key. I'm not going to do this every time with every like limit, like equation that we have, but it's my way of saying if you ever found limits to be sort of abstract in a math class, they do seem very abstract at first. And they maybe seem sort of like very unrealistic or unfair or unclear or something like that. But the weirdest thing is if you start using calculus or thinking of calculus in a physics context, in a scientific context, and if the key difference between science and math is measurement, in a weird way, thinking of things in terms of measurements actually starts making us realize how important and real limits are. Limit, when we say, so from now on, anything, if I say the limit as bleh approaches zero, I mean it's big enough to matter, but it's too small to measure. But it doesn't mean it doesn't affect other, like it matters, but we just can't measure it. So it's the limit as approaches zero. Okay. Um, so therefore, back to reality, snap. Um, oh, sorry, nope, did not mean to say that. Okay. I'm sure many of you already saw where this was going, or many of you have realized this in high school or something, but let me be explicit then. I'm saying you take the average displacement over time, you take that to the limit as the time interval approaches zero, and what you get is the instantaneous velocity. Instantaneous velocity is the limit as time goes to zero of average velocity. Well, when you, anytime now, this is a notation thing. You might want to put this in your notes. Like I'm saying, from now on, ever, the like the connection between math and physics. Here's another handwriting you won't be able to read. Sorry. I'm saying, but this is really important. Piece of notation in general. Sorry, this is almost you can't read this. Not just you. I mean, nobody can. I'm saying, in general, if you have any variable in math or physics, like z, any variable z, what do we mean by dz? We mean the limit as delta z approaches zero. What does delta z mean? It means the finite difference between two values of z. I right? Like slope. Y2 is delta y over delta x. What is that? Y2 minus y1 over x2 minus x1. Whenever we say delta in math or physics, we mean a small but finite difference between two values of some variable. So just look at any variable, call it z. The difference between two values of z, z2 minus z1, or zf minus zi, or z minus z naught, whatever, the difference between two values of z is what we call delta z. When we switch to d, lowercase d, it seems like a big leap. Like all of a sudden, that's when math goes haywire with the d's. But I'm here to tell you when you switch from delta to d, what you're just doing is taking delta to the limit as the variable approaches zero. dz literally means the limit of delta z as it approaches zero. So instantaneous v instantaneous v is dx over dt. Like average v was delta x over delta t. That's what we've been dealing with for the last 2 weeks or whatever. Average v is delta x over delta t. Easier to measure, easier to picture, easier to work with. I know we have. Oh no, we have 18 minutes. Sorry, I keep thinking we have 18 minutes. Oh, we're fine. No, I know we have 18 minutes left. Um, Average v with a bar over it, is delta x over delta t. Now what I'm saying is we started with average because it's actually easier, even though it seems like why we already leaped to that. If we backtrack now to v, instantaneous velocity, it's not delta x over delta t, it's dx over dt. It's shrunken displacement over a shrunken time interval. It's not a finite space interval over a finite time interval. It's an infinitesimal space interval over an infinitesimal time interval. And you know what this thing is called, right? Right? What dx over dt, you know what that's called. That is called the first derivative of position with respect to time. Another handwriting, right? Velocity is a derivative. And I know you know this, but I'm trying to look for some of you who already understand calculus, or some of you maybe, hopefully, understand what I mean by instantaneous velocity a slightly bit better now. Those of you who feel already comfortable with calculus, I'm telling you, what is instantaneous velocity really? It's the first derivative of position with respect to time. That's what the red handwriting says. The first derivative of position with respect to time. Those of you who don't like calculus or didn't like it yet or didn't feel comfortable with it, then I'm saying the reverse. I'm saying, do you want to know how to think of derivatives? You want to know how to think of derivatives? A derivative is an instantaneous rate, as you've heard. It's a rate, it's an average rate, take it to the limit. If you want to picture what a derivative of position with respect to time is, it's what the police officer is asking you when they pull you over. They're not asking you for an average. They're asking you for a derivative, whether they took calculus or not. Right? And the long story short, I know we have 16 minutes. Notice that I do think you could get the answer to number two and even number three without knowing all of this. So I mean, you did need to take calculus to take this class, and calculus will be more and more part of all of our thinking, especially in 204. But I'm actually secretly trying to use the physics now to get you more comfortable with calculus. You can get certain answers without doing a bunch of proofs, but I want you to picture what you're doing. So, takeaway, instantaneous velocity is the derivative, it's derivative, but you can't derivative of position with respect to time. Notice, okay, well, and I prefer this notation. Notice this notation actually means something. If you followed everything I was saying, you may have heard all of it before, but maybe it's in a new perspective now. I'm saying a derivative is a ratio of differentials, right? Each of these little pieces, this piece here is a differential. How can I write? As is this piece, right? Each piece, each D is an infinitesimal difference. It's a difference taken to a limit. It's not out of nowhere. It's not out of a black magic bag. It's a step of reasoning. It's a difference taken to a limit so that the difference becomes infinitely small. That's what a differential is. Not dx, excuse me, not delta x, but dx, or not delta t, but dt. Those are differentials. The ratio of one differential to another differential is what we call a derivative. We measure it with the slope of a tangent line, or we find it on a graph with the slope of a tangent line. So a derivative is a ratio of differentials. Why am I making a big deal of this? You'll know. I'm going to move on now. But again, this is like crash course in calculus or crash connection to the calculus. And again, I want to urge you, for some of you, hopefully you'll use your calculus to understand the physics better. And some of you will use this physics to will understand your calculus better. Either way, you'll know that you're getting something out of what I'm saying. And then I'm going to move on, like checkpoint. If this makes sense to you, what I'm about to write down, or maybe even makes slightly more sense now, you'll know you've just gotten something out of this, or you'll at least know that you're with me. I'm not going to, I'm just, it's a checkpoint. So I'm just going to say it. Whoop. That's supposed to be a bracket. That's a little bit. That piece of God, you've seen that, right? Maybe some of you right now want to throw up. And I don't want that, but that could be true. That thing used to make me want to throw. Like I saw that for a million times in my first level of calculus second. I had to use it for proofs and all that. I hated it. I just memorized it. Sometimes I used it correctly, sometimes I didn't, but it just didn't. But I'm telling you, if you stare at that thing, you know what that is the definition of a derivative, right? I mean, sometimes people write it with H's instead of the delta X's, but look at it that way. If suddenly you look at that and you're like, oh, it's just saying rise over run taken to the limit as the run approaches zero. If you see that, and that's all it's saying a second y value minus a first y value. It's saying the y value over here minus the y value over there divided by the difference in the two x values. It's saying rise over run taken to the limit as run approaches zero. If you can see that, then you see everything I'm saying, that a derivative is just an average taken to the limit. A derivative is just a slope taken off the tangent line. Okay, that said, I know we have 11 minutes. I'm going to get back to the answers on the sheet, but now let me just go one step. So that's an equation now, by the way. Well, really, this is an equation. Like if we're keeping a list of our equations in the class so far, this is a new equation. Average velocity is displacement over time. Instantaneous velocity is the limit of that, is the derivative of position with respect to time. How do you use it? It's just a sorry. Good. I'm so glad there's something in the chat. Really good question. Someone in the private chat is saying, must delta x, I think you're talking about over here, right? Must delta x always have to approach zero? Yes. Great question. For, let me back up. In life, delta x could approach all different kind of limits. Like in life, you could take limits to different things as you have in math classes. But if you're talking about a derivative, if you're talking about, and you're relating it now to physics, like the definition of the derivative, yes, derivative is slope where the run goes to zero. It's the slope of the line connecting 2 points in the limit as those 2 points get so close to each other that the interval between them is practically zero. So, yes, for the definition for that thing right there, if that's what you're asking, the definition, yes, it is part of the definition that the delta x always approaches zero. And that's a great question. If you could let me know whether I was answering the correct question or not, like let me know in the chat and you get more points. But uh, I hope I did. We got 10 more. Oh, okay, cool. Okay, thank you. All right, that's more points. You know how to do, closing a conversational path portal. Okay. Now, how does this have to do with the homework? Oh, okay. So one more thing to relate it back to the homework. Now we have two concepts. We have velocity in general, average velocity between in an interval between 2 points, but then we have instantaneous velocity at a point. We do this, we acknowledge that instantaneous velocity, this whole discussion is occurring because velocity can change from point to point. You have one average to approximate a whole interval, but instantaneous is what's going on at any given moment in that interval. It can change from place to place. So the flip side, right? So that change, that change in velocity from moment to moment is known. That change in instantaneous velocity from one moment to the next is known as acceleration. I'll just say, sorry. And I'm going to, okay. So the equate, so acceleration in English is change in velocity. So mathematically, this is our third equation that we have so far in the class. Okay, right? So we now define average acceleration for now. So in English, roughly, acceleration is change in velocity. Specifically, average velocity, excuse me, average acceleration is change in instantaneous velocity per time. So on the left hand, we have an average quantity that applies to an interval between 2 points. And on the right side, we have the comparison of the two different points. The left side is average acceleration, like there's a bar over it. The right side, there's two different velocities. They don't have bars over them, they're instantaneous velocities. Do you see the structure of these equations that we're developing? And by notice, they're just all definitions. They're not discoveries. We're just making up shorthand terms for longer concepts. Average acceleration is the change in how fast you're going here versus how fast you're going there, divided by time. It's just like average velocity is the change from where you are over here minus where you were over there per time. It's got the same structure, right? So we can go a step further even, as long as I'm just doing all this. We can go a step further. And we can say that instantaneous acceleration would be the this take it to the limit. We could say instantaneous velocity would be dv dt, the derivative of velocity with respect to time, right? I'm making a So velocity is change in position per time. Excuse me. Average velocity is change in position per time. Average acceleration is change in instantaneous velocity per time. It's the same reasoning going up one level. In other words, acceleration is the second derivative of position with respect to time, right? That's another equation. Now I'm going to, oh, something in the chat. Perfect. I know we have 3 minutes. Well, hold on. Let me just, yeah, I'm gonna see the chat. It looks like a good question. What's the, okay, what's, oh, two things in the chat. Oh, sorry. Oh, wait. Okay. Pause for a second. And yes, there was a mistake. And thank you for pointing out. Somewhere in one of these homeworks, I referred to some equation that's in a website or web page or something like, or on the document. My mistake. Just ignore that. Just completely ignore that question. I got to get rid of that. It's from an old assignment in an old website that we don't use anymore. I apologize. So, and please let me know if you're hearing me. Yeah, anywhere you're seeing, if I make a reference to like an equation on the web page or something, just that's my bad. Just ignore me. I apologize. But then there's this, so let me know if you caught that. Then there's this other question. The difference between with a bar and without a bar, very important question. I'm trying to say this a lot, but I'll say it more. With a bar means average. Without a bar means instantaneous. Like from now on in all of these quantities, A with a bar means average acceleration. A without a bar means instantaneous acceleration. Or similarly, V with a bar means average velocity. V without a bar is instantaneous velocity. Let me, either of the two people that were just in the direct chat, they're two different people. Could either of you let me know if I just like acknowledged your, like if I answered your thing correctly? Thank you. Okay, awesome. Yeah, okay, thank you both. So you get points for that. Remember, there's another portal just for the fact you just said that. You get point. Okay, now we only have 1 minute. Here's what we're gonna do. I think I hopefully this was valuable. God knows for whom, but hopefully this was conceptually valuable in putting things together for you. However, I know I didn't give you a lot of answers or work out a lot of stuff on the sheets. So it's like good and bad. Therefore, I recognize that. So therefore, what I'm gonna do right now, if I can, give me 1 second. I'm just looking at the homework assignments. I'm gonna see if I can make a little extension here. Hold on 1 second. The next thing is due September 17th, and then after that. Yes. Oh. Oh, do we have school next Monday? Wait a minute, we don't have school. Yeah, well that's what I'm looking. That's exactly direct type person. Wednesday. Okay. So I'm gonna no holidays Monday, Wednesday. Okay, I'm gonna make an extension on the next homework. Let's do because I know now it's sort of my turn. So you've already had to do some stuff without me. I recognize that. And some of you have already handed in Wednesday. That's awesome. But if you feel like you know what you're doing, you could take more time and do more of it or whatever. But I'm going to extend it right now so that you all have time to catch up and I have time to catch up with you. So it was due Wednesday. Sorry. Why? Where'd it go? Oh, okay. So we don't have, oh, yeah. I mean, this is going to be long, but all right. I'm extending it to the 29th. So you all have some, so catch up. We'll all have catch up time. Then we will have to move fast after that. But what else, what was due? And I know it's class is over. All right. So I just extended the homework for anybody who's okay. You're welcome. Okay. So, but that's a lot of time in a way that was slightly dicey that I just did that. But, so do whatever you can I think you still can do a lot of without what I've talked about. But anyway, yeah, so I just extended it. So it's not due this Wednesday. Okay. So, well, I extended it till the very first day you come back after the holidays. So it's Monday I just changed it to Monday the 29th to the 29th. Okay. So I know you all have to go now. I mean, you can hang out for a second if there's more questions to ask. I'm here, but so and you'll see in Google Classroom I extended it. Okay, so I'm going to stop. So I'm turning off the recording. I'm here if you have any questions.